Welcome back to AP/BC Calculus. This is day 4. Today we're talking about sections 2.3 and 2.4. Okay. To get started, we have a warm-up. So if you can see, I have the graph of a function f shown, and I'm asking which of the following statements is true. So take a moment. So the first thing we see here is that there are two holes in the graph, A and B. However, at B, the graph is defined. It's defined at 1, or as 1 at B. Okay. So going through the choices, let's see, A, the limit of f of x as x approaches A and the limit of f of x as x approaches B is the same. Well, that's obviously not true. You can tell right off the bat that the limit at B does not exist because the limit from the left and the limit from the right have two different values. So immediately we can cross off A. We should be able to cross off B or D since we said that the limit at B did not exist. So it is neither of these. The question is, does this limit exist? Is it okay for the limit of a function to exist if the value of the function doesn't exist? Yes, it is. So B would be the answer here. The limit of f of x as x approaches A is 2, because the limit from both directions at A is 2. It is not defined at 2, but that's okay. So today should be somewhat of a review. We're talking about power rule, quotient rule, product rule, rules for differentiation that you should have seen at the end of calculus honor or pre-calc honors last year. But if you happen to not have been in that class, then maybe you didn't get it. So we're going to review it today. Okay. So we're going to start off with power rule, and what I've written up here is the extended power rule. All that means is that r could be any real number. The power rule traditionally refers to the exponent as being some integer, but really it could be any real number, like pi or e, right, not I. So in the first example, part A, let's see, this is just straight up power rule. Okay. I'll use a multitude of notations for derivatives, but typically I like primes. Okay. Drop the power down, multiply, decrease the power by 1. Drop the power down and multiply, decrease the power by 1. The derivative of a constant is 0. Answer. B looks like it might use quotient rule, but what we're going to do is go ahead and divide through by that square root of x, which is really just x to the 1/2 power. Okay? So we'll rewrite this as, so x to the 3rd over x to the 1/2 plus 6x over x to the 1/2 minus 2 over x to the 1/2. All right, and now we're just going to simplify a little. See, 3 minus 1/2 is 2.5, or x to the 5/2. Okay. 1 minus 1/2 is 1/2, or x to the 1/2, and then this will leave as x to the negative 1/2. All right. Let me get my equal sign. All right, now we can just do power rule as described above, where we drop the power down in front and then decrease the power by 1. All right, so 2/2 minus 1 is 1/2. 1 and 1/2, excuse me. plus half of 6 is 3. Decrease the power by 1 gives me a negative 1/2. Minus half of 2 is 1, but it's a negative half. Makes that a plus. X 1/2 minus 1 is negative 3/2. Okay. And do I need to go through and change all of the negative exponents? I could, but I'm not going to. I'm just going to remember that, I know that the negative signs are there, and if I went through and tried to and made a mistake, then wouldn't that be a shame? All right. So answer. So the natural exponent e to the x is one of the greatest functions out there, because it is its own derivative, which is pretty fantastic, and one of the main reasons that it's used so frequently in differential equations, which we won't necessarily get into in this class, but for the future, that's the reason why. So yeah, e to the x is its own derivative. So for this example, straight up power rule first. Let's do dy dx, just to change things up a little bit. 16x minus 7 e to the x. All right. So next up is the product rule. The product rule says that the derivative of the product of two functions is the derivative of the first times the derivative of the second, plus the second times the derivative of the first. And obviously, since addition is commutative, if you said second times the derivative of the first plus the first times the derivative of the second, it would be an equivalent statement. So whatever one you learned is fine. So let's look at an example here. For this, I'm going to actually show what the first and the second are. I typically won't do this. This is my first, and this is my second. All right. So first, times the derivative of the second. The derivative of the second is just e to the x, because we just talked about how e to the x is its own derivative, plus the second times the derivative of the first. The derivative of the first, we're just using power rule. Okay. And then if you'd like to clean this up by pulling an e to the x out, that's perfectly okay. And I'm left with x cubed plus 3x squared minus 2x minus 2. Easy as that.
Easy as that.
All right, to round out the theorems for the day, next up is the quotient rule, everybody's favorite. So the quotient rule says that the derivative of the quotient of two functions, f of x and g of x, for example, is given as the bottom function times the derivative of the top function minus the top function divided times the derivative of the bottom function all over the bottom function squared. However you remember that, ho-de high, lo-de high, that's up to you. Just make sure that you get it right. So the first example, g of x equals 2x plus 3 over x minus 1. We're going to have the bottom, which is x minus 1, times the derivative of the top, which is just 2, minus the top times the derivative of the bottom, which is just 1. And then we'll have the bottom squared. So to sort of clean things up, we have a 2x minus 2 minus 2x plus 3, which is negative 2 plus 3, 1 over x minus 1 squared. All right. B is a little bit more tricky because it has another rule that we have to take into account. So let's just go ahead and start. I'm going to use a different color so that we don't get the two examples confused, because this might run over. So h prime of x is the bottom times the derivative of the top. Now the top is a product of functions, right? So let's go ahead and look at what the derivative of the top is. Let's call it f of x and write it out. So it'd be the first times the derivative of the second plus the second times the derivative of the first. So we can clean that up and say that it's e to the x times 2 plus 2x plus 3, or 2x plus 5. So now when I say the derivative of the top, I know it's just e to the x 2x plus 5, okay, minus the top times the derivative of the bottom, which is just 1. And then of course this is all over the bottom squared. Okay. Now let's clean things up just a little bit. And we can pull in e to the x out. Let's see. There's not much else I can do. I could expand this. Get 2x squared, right? Plus a 5x minus a 2x. 5x minus 2x gives me a plus 3x. Okay. Minus 5 minus 2x plus 3 all over x minus 1 squared. And just one more step to make things look real nice. E to the x times 2x squared, 3x minus 2x is just 1x, negative 5 minus 3, negative 8. Squared. There's my answer. Okay? Now, some people might ask, could I stop here? Absolutely. You could absolutely stop there. And in fact, unless you have to do something with this derivative later, I would always stop there. I wouldn't do the algebra to try to get it to look nice and pretty. The only reason you're going to get it to look nice and pretty is if A, it's a multiple choice question and you don't see this answer in your answer choices, or B, you need to do something with it after you found the derivative. Okay, you were asked to find, I don't know, the slope of a tangent line at a given point. This might be easier to manipulate to plug numbers into or to set equal to something or something of that nature. But this would be a perfectly acceptable answer. Okay? As long as you've shown that you've done the quotient rule correctly, obviously. Okay. So in example 5, we're asked to find this d2y dx2 thing. And if you're unfamiliar with that notation, it's really just asking for the second derivative. Okay? This means to take the second derivative of y with respect to x twice. So that just means that we're going to find r prime first, and then r double prime, which is the same notation. Well, different notation, but same thing. So instead of doing a quotient rule here, which I could do, I would recommend against that, just because it's so simple to just turn this into x minus 1 to the negative 1/2 and go from there, right? So let's see, r prime. Unless I erased the prime on that r, because all I was doing was rewriting r. Now I'm going to find the derivative by bringing the negative 1/2 down and decreasing the power by 1. Okay. And let's just do it again. R double prime, or the second derivative, okay, would be a positive 3/4, right? Negative 3/2 times 1/2, x minus 1 to the negative 5/2. And that would be my answer. Now, there is just one slight thing that I'd like to clear up here. Not a big deal, but see, this says take the second derivative of y, and we technically haven't defined y. Maybe this says y equals a function r of x, or y is defined as a function r of x. Then we're okay. Otherwise, it would be find the second derivative of r of x with respect to x. Just a subtle nuance, nothing to really get all upset about, but example 6 gives us a function f of x, or y is equal to f of x, 5x to the negative 2, and asks us to evaluate this funny looking thing. So if you're unfamiliar with this notation, again, this is the third derivative of y with respect to x, and it's telling me to evaluate where x is equal to 1. So maybe a more familiar notation to some would be, what is the third derivative of f evaluated at 1? That's really what we're looking for. So let's get started with the first derivative of f, which is negative 10 x to the negative 3. All right. The second derivative of f, which will be positive. It's the negative 3 times the negative 10. Positive 30 x to the negative 4. And then the third derivative of x would be a negative 120 x to the negative 5th. Okay. Now we're asked to plug in 1. All right. Well, I just get 1 there, and I'll end up with negative 120. Easy as pie. For the last example we have today, a little bit of an application. Find the equation of the tangent line to the curve at the given point. So here's my curve, which I've already graphed, and here's a point on that curve. And we want to illustrate the result by graphing both the curve and the line in the same viewing window. And you can do that at home on your own graphing calculator and get a better picture than what I'm going to have here by graphing by hand. So for the equation of a line, I need two things. I need a slope and a point. I have the point. Let's get the slope. Okay. To find the slope of a curve at any given point, I need its derivative, or its rate of change. In this case, I have 1 plus 1/2 x to the negative 1/2, or to sort of clear things up, it's this. Okay, so what is the slope at 1, 2? Well, it's whatever we get out of that derivative function when we plug in 1. Okay. It's 1 plus 1/2, or 3/2. Okay. So now that I have my slope and my point, the easiest form of the equation of a line to use would be point slope. Okay. So we'll define another line as L. We won't do that. We'll just keep it as point slope and say it'll be y minus 2 equals 3/2 x minus 1. Alright. So what is that going to look like over here? Well, it definitely goes through the point 1, 2. It has a slope of 3/2. So up 1, 2, 3 over 1, 2. Oops. 1, 2. And then let's do down 1, 2, 3 over 1, 2. So let's see. Sort of like that. Okay. So as you can tell, my line is somewhat tangent to the curve. And if you were to graph this on your own graphing calculator at home, you would see an even more obvious result.